Welcome to Chemical Reactor Design. Today we're going to design CSTR with heat effects, where we're going to calculate the resulting conversion and temperature for a specified volume of a CSTR. Basically that's example 8.8. Okay, so as you recall, we say we have almost three major cases when it comes to the design of a CSTR with heat effects. The first two cases, we have sequential calculation, and the last case, where V is specified, we need to calculate X and T in a simultaneous calculation. That's the case we're gonna discuss today. Example 8.8, production of propylene glycol in an adiabatic CSTR. Okay, so propylene glycol is produced by the hydrolysis of propylene oxide, of course in the presence of a catalyst, homogeneous catalysis we have here. So as you can see, this reaction where we have propylene oxide reacts with water in the presence of a catalyst to give you propylene glycol. This is very similar to the reaction that we have discussed in example in chapter 4, where we did the hydrolysis of ethylene oxide to produce ethylene glycol. Over 800 million pounds of propylene glycol were produced in 2006, and the selling price was approximately $0.68 per pound. Propylene glycol makes up about 25% of the major derivatives of propylene oxide. So if you take propylene oxide, the total amount of propylene oxide produced per year, you'll see that 25% of that goes for the production of propylene glycol. The reaction takes place readily at room temperature when catalyzed by sulfuric acid. You are the engineer in charge of an adiabatic CSTR producing propylene glycol by this method. Unfortunately, the reactor is beginning to leak, and you must replace it. You told your boss several times that sulfuric acid was corrosive and that mild steel was a poor material for construction. Of course, you remember from the course properties and strength of material what mild steel is. Mild steel basically is a low carbon steel. So the content of carbon is very low, somewhere between 0.05 to 0.25% only. And it's actually the most common form of a steel because its price is relatively low, while it provides material properties that are acceptable for many applications. However, Shabab, mild steel has a relatively low tensile strength, and of course, it can be corroded, but it's cheap and easy to form. Okay, back to our course. There is a nice looking overflow CSTR of 300 gallon capacity standing idle. It is glass lined and you would like to use it. So now you can see that it's much better material of construction because it's lined with glass, so it will not be corroded. Okay, let's get to know more about the process. Okay, feed process variables are as follows. What do we have? Well, we have stream, of course, stream 0 going to the reactor. Then we have two other streams which are mixing to form stream 0. So the first stream we call it 0,1. Second stream we call it 0,2 because they mix together to form stream 0. Okay, so let's look at stream T01. Okay, and stream T01 actually consists of two other streams. Okay, what are these streams? Well, we have propylene oxide, which is coming with this total number of moles. So this is Fa01, and this is the volumetric flow rate. And then we have the other stream, which consists of methanol, and coming into the system with this volumetric flow rate, which corresponds to this molar flow rate, which you can find after using the molar well, we have to use the density here and then use the molar mass. Okay, طيب, so this is the stream 01. Let's look at stream 02. Well, it consists of water, mainly water, with some addition of sulfuric acid, which is the catalyst. Okay, and it's coming in with this volumetric flow rate, and then you can calculate its molar flow rate again with using the density and the molar mass. Okay, so the question now is, I'm sure you're asking, what methanol is doing here, right? You say, well, water is my reactant and water is my solvent, but what methanol is doing here? Well, the fact is methanol is added to prevent phase splitting. So why is that? Because propylene oxide is not completely soluble in water. Therefore, to prevent phase splitting, to prevent having two phases where you see that propylene, not all of propylene oxide is soluble in water, we add methanol. Now the whole mixture becomes soluble and homogeneous. Okay, طيب, and let's see, we have water and methanol. We have water and methanol. Remember what methanol and water form? Well, although methanol is completely soluble in water, but they form an ideal solution. So now the properties are not additive. تمام? The properties are not additive. And let's look what's happening here. Both streams 01 and 02 are entering at 58 degrees Fahrenheit. Okay, however, when they are mixed, the temperature jumps all the way to 75 degrees Fahrenheit. What just happened? Well, obviously there was no enough space for reaction to happen. It's only a mixing point, a small mixing point. Okay, if you can see it here, mixing point. Tamam. It's a very small mixing point, so there's no really space or volume for reaction to take place. So this increased temperature was not due to reaction. What was it due to then? Well, it was due to delta H mixing, because this new solution which is formed here actually cannot hold enthalpy of this stream. Okay, the enthalpy of this stream, which is the enthalpy of stream 01 plus the enthalpy of stream 02. Of course, both were saying at 58 degrees Fahrenheit. So this stream, which is stream 0, actually cannot hold the enthalpy. Okay, so the enthalpy of the constituting streams, which is stream 01 and 02, is much more than the enthalpy of the mixture, which is stream 02. So what happens? So if this is your cup, okay, and then you're adding this energy into this cup, but this cup actually corresponds to the mixture. So, but you're adding a lot. So what happens? It will overflow, right? Because you're adding more than what the solution can hold. So it will spill off. The energy will spill off, what will happen? Again, you don't have enough area here to transfer all of this heat, extra heat. So it will stay inside and will raise the temperature of the system. Okay, and now that this mixture, which is stream 0, is at 75 degrees Fahrenheit, 75 degrees Fahrenheit. Now the enthalpies are equal. Okay. طيب, again, this is due to the formation of non-ideal solution. Okay, what next? Well, we know that it's a non-ideal solution, so we know that the volumetric flow rate is not additive. In other words, epsilon naught cannot be calculated from epsilon A01 epsilon M01 plus epsilon B02. We cannot just simply add the volumetric flow rates here, tamam, to get the total volumetric flow rate here. In fact, the actual volumetric flow rate of epsilon 0 or epsilon naught is 3% less, and that's also something we noticed from our experiment. Please go back to the previous lectures, which I think it was lecture maybe 40 or 39 or something like that, or maybe 41, for more information. طيب, what else? So let's assume that the volumetric flow rate is additive. Okay, So again, remember Shabab, we have the volume. We have the volume specified for this reactor. Okay, what is remaining? Well, we need to calculate X and T. Okay, so V is given. This is article number 1. Article number 2 in the design is where the missing information is, which is to find X conversion and T. Okay, what other articles are for the design? Well, we need the conditions, right? We need a condition. So all of these conditions are given here. What's the last article of the design? Well, we need the kinetic and the thermodynamic data. So let's do that. Let's bring those data. Kinetic data. In similar conditions, the reaction is first order in propylene oxide. So it's first order in A and zero order in water, zero order in B. Why is that? Because I'm providing B in excess. I'm providing water in excess. Okay, what else is given? The Arrhenius equation is given for K as a function of T. Okay, so let's go to thermodynamic data. We have here, we can actually extract from the literature the following data. We can find the CPs, all the CPs, and also the delta H formations. Where we need the delta, why we need the delta H formation? Well, basically to calculate the delta H reaction. Okay, propylene oxide is a low boiling substance. Wow, the boiling point, the normal boiling point of a propylene oxide is only 34 degrees C, very low boiling point. So to prevent losing it through vaporization, you shouldn't exceed an operating temperature of 125 degrees Fahrenheit. So the temperature inside the reactor, should not exceed 125 degrees Fahrenheit. Why is that? Because the propylene oxide is a low boiling point substance. It's a substance which has a low boiling point. Okay, so one would think, how come the boiling point is 93 degrees Fahrenheit of propylene oxide and you're saying we shouldn't exceed 125 degrees Fahrenheit? Shouldn't you say we shouldn't exceed 93 degrees Fahrenheit? Well, remember, we have a solution here. The solution inside the reactor consists of 4 species. Consists of propylene oxide, water, propylene glycol, and methanol. So all of this mixture, the boiling point of a mixture or the bubble point of a mixture will be now different, right? So the species will not boil off. It's not like every individual species will only boil at their respective boiling point. No, that's not true. Please refer to the thermodynamics of solutions to remind yourself of this. So the bubble point will be somewhere between, roughly speaking, will be somewhere between the lowest boiling point of the species and the highest boiling point of the heaviest species. Okay, طيب. So basically we shouldn't exceed 125 degrees Fahrenheit. Okay, what is the question? Can you use the ideal CSTR as a replacement for the leaking one if it will be operated adiabatically? So can we use this reactor, which is shown in the picture here? Tamam. Can we use this reactor and operate it adiabatically and still maintain a temperature below 125 degrees Fahrenheit? If so, what will be the conversion of propylene oxide to glycol? Okay, so basically we need to calculate X and T and then compare the T to the constraint, which is T equals 125 degrees Fahrenheit. Shouldn't exceed 125 degrees Fahrenheit. Okay, so let's do this. Let's solve this problem. Well, actually, before we proceed with the solution, I would like to invite you to read this very nice article, which is written by a few authors from the University of Pennsylvania, and it's about the batch manufacture of propylene glycol. Very informative article. طيب, let's go to example 8.8 again, and let's solve it. Let's find the x and t. Okay, solution. So illustrate the solution graphically and provide the table used. So now we want to solve this problem, finding the required information, which is x and t. We want to use the graph. And also, of course, if you're going to use a graph, you're going to use a table to plot, right? So we're going to do this. Right. So we start from the material balance. Okay, as usual, we start from the material balance, from the design equation. And as you recall, Shabab, now we have two unknowns, right? X and T. That means we need two equations. First one is the material balance, the second one is the energy balance. We need to solve them simultaneously. So therefore, we're going to write the material balance and solve for X. Call this X, X and B. And then use the energy balance and solve for X again, and call this X, XEB. تمام? And then we're gonna plot these two functions. طيب, so the mole balance, this is the mole balance. تمام? So let's write X and B as a function of temperature only. Okay, I believe that you know how to do this, so I'm going to leave it to you. Of course, you will, after writing the design equation, you will write the rate law, and then you will write the stoichiometry, and then you will combine all of the above into the mole balance, and then you will solve for X. I'm not going to go into details here. You have to do this by your own hand. Okay, so here we go. X and B equals tau k over 1 plus tau k. Do you memorize this equation? Absolutely not. This is very specific to this case only. Tamam? So not always X and B equals tau k over 1 plus tau k. Okay, so let's substitute for k. Let's substitute for k. And you know that k is a function of temperature through Arrhenius equation. And you can see it here in this equation. Right. Next, we go to energy balance. So here we go. That's our energy balance. The reactor is operated adiabatically, so this goes to 0. We will assume negligible shaft work. Okay, negligible shaft work. Although it's a CSTR, we're adding work to the system by the movement of the shaft, but we're gonna assume it negligible. And of course, what else? We need to calculate delta Cp, because delta H reaction is function of T and delta Cp is not 0. And what else? Let's go to theta I. So how many thetas you have? Well, again, when you have theta, you have to look at the feed. We do not look at the stoichiometric reaction, the stoichiometric equation. We look at the feed. How many species do we have at the feed? Well, basically, we have 3 species. We have water, propylene oxide, and methanol. Don't forget the methanol. Okay, good. So let's write this equation in terms of temperature. So let's solve it explicitly for X, and we call this X, XEB. Okay, here we go. Tamam. And for simplicity, Shabab, you can call this term, you can call it CP naught. Okay, you can call it CP naught. Okay, and then we substitute for all the knowns. Okay, so we have to calculate the Cp naught. We have T naught. We have to calculate delta Cp. The T reference is also given. Tamam. We also need to calculate the delta H reaction from the delta H formations. Okay, now we have two equations. We have X and B as a function of T, تمام. And we have XEB also as a function of T. So let's plot these. How do we plot them? Basically, before we plot them, we need to use a table, construct a table. So let's learn how to construct this table. We're going to use Excel. So please make use of the features. Okay, make use of the features of Excel. So in this table, we're not gonna enter all the parameter values. The parameter values, we're gonna enter them on separate cells, as you can see. So do not include the numerical value of parameters shown on the left into the XMB and XEB cells. Don't forget to fix their cells value using the F4. So what do you do, for instance? Okay, so we enter all the parameters here. T naught equals 75 degree Fahrenheit. I convert it to Rankine. The same with TR is 68 degree Fahrenheit, converted to Rankine. And then see this epsilon naught. Okay, this epsilon naught. Actually, even this epsilon naught, we do not really enter its value here. What do? You link it to epsilon 0, epsilon A01, epsilon M01, epsilon B02. So we sum up all of these, we enter all these epsilons, and then this cell is basically summation of the other three cells. What about the V? Well, the V, we enter it here, and then we convert it automatically to cubic feet. Tau, I did not enter the value of tau. What I did simply is I took the volume, this volume, and divided it by epsilon. Okay, and then we entered the value of Arrhenius constant, enter the value of E, the R, and then I entered these values. Actually, even these values, you can avoid entering them by using the respective volumetric flow rate, the respective density, and the respective molar mass. You can do this. Okay, and then automatically I will calculate the thetas. So these are not entered. These are linked to theta, this theta and that, this F and this F. So let's look at theta M, for instance, this guy, theta M. Basically, I took the value of Fm naught, this guy, and divided it by Fa naught. And the same here, I entered the CPs, the CP values, and then I calculated this value, Cp naught, or the summation of theta I Cpi, from the above values of Cp and the theta values, and delta Cp again I've calculated from the above, and delta H formation. Also, I did not enter this value. Here actually it's an equation consisting of the delta H formation of the others. Okay, so we're gonna plot XMB and XEB, as a function of temperature. So that means you have to vary temperature and calculate XMB and XEB. So I varied temperature. Okay, I started with 75. So I linked this guy, I linked it to this guy. Okay, and then added 2.5 degree Fahrenheit in each. Actually, it's 2.5. That's why you can see the values increasing. Anyway, maybe there is some difference here, but anyway, I added an equation to increase the temperature, and automatically the T at Rankine will also change. And then I calculate the value of K. How do you calculate the value of K? Well, here there's an equation embedded here, and the equation is basically I go and choose this cell. After I choose this cell, I press F4. What does it do? It will fix the cell. So when I drag it, it will not drag to the next cell. So that's the cell times e to the power minus, and then I choose this cell and press F4. Okay, so that's divided by R, again choose the cell, fix it, divided by T, and here I choose this cell and I don't fix it. So this is something I want to change, and then I drag it down, and so on. Okay, and so the same thing with delta H reaction, the same thing with XMB. So XMB is tau k divided by 1 plus tau k. So I do not really enter the value of tau. I link it to this cell here. Tamam, and I press F4, and then k is linked to this cell, and I'm not fixing it. It's supposed to vary, and so on. Okay, so this is how I construct this table. Okay, now I can plot. Now I can plot XMB and XEB as a function of temperature. So here we go. There we go. That's X versus T in Rankine. And you can see that the XEB looks like to be a straight line, right? Although you look at the equation, it's not, but because the delta Cp is very small compared to delta H reaction, that's why it does not affect how the equation looks like. Okay, and always, Shabab, XMB is like an S shape because it has to level off at 1. Okay, so from here you can see that there is a solution, which is this value of T. This value of T. So this value of T satisfies both equation. So if you put this value of T into XMB or XEB, they will both give you the same value. Tamam? So that's the solution. That's the resulting temperature and conversion. That's the resulting temperature and conversion. If I run this reaction with the given conditions into this reactor, which is operated adiabatically and has a volume of 300 gallon. So what's the exact answer for X and T? Well, we go back to the table and we use a solver. So as you saw there, Shabab, roughly the answer from the figure was around 310 Rankine, and X were above 0.8. So let's say, whatever it is. Okay, so if we want the precise answer, we can use solver to find the precise values of T and X at the steady state. So what do? We use solver. So we go to a cell. Which gives you, so let's look at the value of this cell. The value of this cell originally was around 150. Okay, so, and I said, okay, yeah, this is where XMB seemed to be equal to XEB, and this is where, remember, the around 160 should be the solution. Okay, so I come to this cell and I use solver. So how do you use solver? You go to data and then you go to solver, and then what do? Do you start with set objective? No, we don't start with this sentence. We start with this sentence. By changing variable cell, which cell? The cell. Come on. By changing the variable this cell. Okay, and we set a constraint. What's my constraint? My constraint is that XMB should equal XEB. So that's I add here. I add a constraint, and then I press solve. And when I press solve, automatically changes the value of this cell, which originally was around, I think, 150 or something. Changes automatically until XMB equals XEB. Because you see, before this, XMB does not equal XEB, and after this, XMB does not equal XEB. It's only at that specific value. Okay, so now we found the precise solution. So T is 153 and the obtained conversion is 85%. Okay, but unfortunately this temperature, which is the steady state temperature inside the CSTR, which is 153 Fahrenheit, exceeds 125 degree Fahrenheit constraint big time. So that's bad. I cannot use the reactor as is, because the temperature inside the reactor will be much higher than my constraint, my limited the temperature, the temperature limit which I had put for myself. Because otherwise, if I run the reaction in this reactor, the temperature will reach to 153 at steady state, and I will lose a lot of the propylene oxide. So what do I have to do? Well, هذا ما سنشاهده في الحلقة القادمة. Stay tuned and join us in segment 2.